Okay, good day. This is Mr. McCulley. This is AP Calculus. This will be the lesson on section 2.1, the limit definition of derivative. So let's get started right away here. All right, so our goals for this section will be to use the limit definition to find a derivative, to use the derivative to find the slope of a tangent line of a function, and use the derivative to find a rate of change, which we will be discussing more in class. So first thing I would like you to do is, this is a calculus help video, and I'm going to put the link to this in the description, but you can read it right here and click it. And I would suggest that you take about 5 minutes to watch the whole thing and talks about the derivatives. And the best thing about this is it gives an animation that I really can't do in this particular section, and it does a real good job to give you a general idea of what we're trying to accomplish when we're talking about the limit and as we let delta x go 0. So press pause, go down to that, and then take a look at it, and then we'll come back after you're done and start again. So 5, 4, 3, 2, 1, moving on. So hopefully you watched that video and you got a general idea of what we're trying to do with this limit definition of the derivative. And so in general, here's what we're trying to do here. We have this function, and we're going to eventually call it f of x. And let's say that I'm trying to find the slope of this function, f of x, at this point. And that tangent line, let's color it. Let's make it kind of small. And let's see here, give me the properties of that thing, make it red. There we go. And draw that tangent line. So what I'm trying to do here is trying to come up with that tangent line. And the best that I can do is pick another point that's along this point here and come up with a secant line. And that secant line will hopefully look like this. And it'll be kind of like what he drew in the other diagram there, or the animation diagram. And as I let this point right here get closer and closer to this first point here, my blue secant line will get very, very close to this red tangent line. Now I know that this limit exists because I can draw in that tangent line. That tangent line does exist. And so we want to make sure that we get something real close to it. So how do we do that? Well, if I label this point right here x1, y1, and this point here x2, y2, then I can use this particular slope, definition that you learned way back in probably 7th or 8th grade. Now, how does that work in the context of a function? Well, let's see if I can't get this to come up for me. It's not going to, but that's all right. We'll just erase some of this stuff. Come on. Erase my eraser. Erase that. Oh, I think that's what's going to happen. All right. Looks like I'm going to have to redraw it. That's it. Maybe I'll get away with it. Okay, there we go. So here's my function. Here is my value right here. I'm going to call this point right here. This is my x, and the distance to that here is my delta x. So this point here has an x value of x, and this point right here has an x value of x plus delta x. Now how do we get the y value? Well, we take whatever we had for x, we plug it into the function, and that's what we get y. So we're plugging it in for f of x. So this is f of x because that's how we find y. Now for this particular x value, we're plugging this whole expression x plus delta x in for f of x. So I'm trying to rewrite this just a little bit more neatly so we can see it. It'll be x plus delta x. That is the x value. It's from here, plus this additional, and this kind of stinks too, so let's make it a little bit better. There we go. And so its function value, I plug all of x plus delta x in and get f of x plus delta x. Now, this thing up here represents my 2's, so my y2 is represented by this expression here. My y1 is represented by this function here, so we go from y1 to y1, or excuse me, y2 to y2, and then this is y1 to y1. This is my x2, this is my x1, so I replace x2 with x plus delta x, and I replace x1 with x. Now, positive x and negative x cancel, so these things cancel out. So this right here, this expression right here, is the slope of this blue secant line. And when we let the delta x shrink to 0, now we have the equation of the first derivative. And we can calculate, we can use the equation of the first derivative to calculate the slope of the tangent line at a given point. So there's my formal definition. Definition of derivative, the derivative of a function at f of f at a point x is defined as that limit definition, and you need to memorize that. And then there are a number of different ways that we can describe a derivative in different notation, and we are going to use pretty much these first 1, 2, 3, 4 quite extensively throughout the year. This one is used a little bit later and when you get into higher level calculus, but it's in our book, so I threw it in there. So this one, these first three actually represent the derivative. This one here says take the derivative of f of x. So it's a little bit different than the first three, but they're all essentially the same thing. All right, so differentiability implies continuity. So if a function is differentiable at a point x, then it is continuous at x. The converse is not true. All right, if it's continuous at x, it does not necessarily have to be differentiable at x. So points where there are sharp turns or places where there are vertical tangent lines are going to be places where you're going to have no differentiability, but it could still be continuous. So our example here is, given the following function, use the limit definition of derivative to find the slope of the tangent line at the point 1, 5. So before we actually get into this question, let's talk about what it's asking us to do. We have this function here, f of x equals 6 minus x squared, which is clearly a parabola because it's a second degree polynomial. Its leading coefficient is negative, so it opens down and has a y-intercept of 6. So we have a general idea that it's going to look something like this. All right, so 1, we'll say that's a 5. There's our 6. I'm going to say right here. So we're trying to find the slope of that tangent line. All right, so we know from the reading that the derivative finds the slopes of tangent lines at given points. So that we're going to start with this limit definition, and we're going to say that f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now clearly, if we let delta x go to 0, I get f of x minus f of x, which is 0, and I get 0 on the bottom. So if we did a direct substitution in the limit form, we would get 0 divided by 0, which is undefined. So we have to do something about that. And that's kind of what we're doing with all of the limit definitions of derivatives, is we're trying to figure out a way to cancel out that undefined value. So let's plug in. I've got my limit, and again, I haven't evaluated the limit, so I do have to write it at every step until I actually evaluate the limit. So we're plugging in. Well, the 6, we're plugging in for f of x plus delta x. The 6 doesn't have a variable to plug in for, so we're just going to put a 6 there. And then we're going to go minus, well, we get x plus delta x squared. So we're plugging in x plus delta x in for x. And then we're going to subtract away from that just f of x. Well, f of x is just 6 minus x squared. And that's all over delta x. So we want to simplify if we can. And again, we're trying to cancel out that delta x on the bottom so we don't have an undefined. We still have not evaluated the limit, so we need to write it. And so I've got 6, and then I FOIL that out, so it becomes minus x squared plus 2x delta x plus delta x squared, and then I distribute the negative, so I have negative 6 plus x squared all over delta x. And let's rewrite one more time. So the limit as delta x goes to 0 of 6 minus, and I'm going to distribute that to that negative to each term in here. So minus x squared minus 2x delta x minus delta x squared minus 6 plus x squared. Now, this still stays all over delta x. And let's see what cancels. I've got a 6 that cancels out with a negative 6, an x squared that cancels out with an x squared. So that's going to leave me the limit as delta x goes to 0 of negative 2x delta x minus delta x squared all over delta x. Now here's the position we want to be in, because every term has a factor of delta x in it. So we can cancel out a delta x and say that the limit as delta x goes to 0 becomes negative 2x minus delta x. Now, in this case, because we've canceled all those values out, if we let delta x go to 0, we no longer get an undefined. So now it just, and again, we're evaluating the limit now, we're letting delta x go to 0, so it's just negative 2x. So we can say that f prime of x is equal to negative 2x. This is the function that finds slopes of tangent lines. And so what we can do is we can take that x value, this one value for right here, and plug it in. And so if I go f prime of negative 1, or excuse me, positive 1, I get negative 2 times 1 is negative 2. That is the slope of that tangent line, and even though I didn't draw it to scale, it still seems reasonable because we did draw in a slope or a tangent line that has a negative slope. All right, let's look at this one. This one's kind of a doozy. It is the hardest one in that section. It's the last one in this section. And this section basically says use the limit process to find f prime of x. All right, so I'm not going to rewrite that limit process. I'm just going to plug it in. And again, if you want, you can always go back, and there it is. So in this case, f prime of x is going to equal the limit as delta x goes to 0 of, it's going to be 4 over the square root of x plus delta x minus 4 over the square root of x. So this is f of x plus delta x. This is f of x. It's all over delta x. And so we've got fractions and fractions. We got radicals. We got all kinds of things. And again, if we let delta x go to 0, it's still undefined. So let's start trying to get this down into one fraction. So the first thing I want to do is I want to combine the fractions on the top. So I have to use a funky one. And so that's going to look like this. It's going to look like the limit as delta x goes to 0 of, well, let's see here. I gotta have a common denominator, so I need, it's gonna end up being square root of x times square root of x plus delta x. So I'm gonna multiply this one by square root of x over square root of x. It's still gonna be 4 over square root of x plus delta x. And then this one will be, or it'll still be minus. Come on, let's just get it right. First time, no errors. Minus 4 over x, or square root of x, times the square root of x plus delta x over the square root of x plus delta x. All right, and that's still, oh, don't forget that, still over delta x. All right, so simplifying. Now we have the limit as delta x goes to 0, and I would have 4 delta x minus 4 square root of x minus 4 square root of x plus delta x. And I'm not going to multiply what's underneath out. I'll leave it for right now. So I've got square root of x times the square root of x plus delta x. And that's still all over delta x. Now, when you have a fraction divided by a whole value, it'd be like delta x over 1. We flip it and multiply. We can move that to the top. So in that case, I'll have the limit as delta x goes to 0. And I'm just going to do the bottom here real quick. So this delta x, it kind of just moves up to the top, or it moves up to the bottom of this fraction here. And so I have delta x times square root of x times square root of x plus delta x. Now, here on the top, I have a 4 and I have a 4, and I'm going to factor out that 4 simply because it's going to make my next step a little bit easier. So I'm going to have square root of x minus square root of x plus delta x. Now, at this point, I have it down to a single fraction, and so I need to rationalize the numerator. All right, and I'm going to use a conjugate. And it's another funky one. So this one right here, I'm going to go square root of x plus square root of x plus delta x over the square root of x plus square root of x plus delta x. I have that. That's my multiplication here. And remember, so a plus b times a minus b is equal to a squared minus b squared. And so that's going to leave me with a limit as delta x goes to 0 of 4 times, now square root of x times square root of x is just x, and then it will be minus square root of x plus delta x times square root of x minus plus delta x is just going to be x plus delta x, and that's going to be in parentheses there. And then this on the bottom will still have my delta x. I still have my square root of x, and then I have my times square root of x plus delta x. But now I have multiplied by this whole expression, which is square root of x plus square root of x plus delta x. I told you this one was a tough one, and it is certainly that. Now, here's the good news. Good news, good news. X minus x, those cancel. I can just go boom, boom. Now, this thing here will leave me 4, because it's 4 times what's inside these parentheses. It'll just be 4 delta x. 4 times delta x. And since it's all multiplications here, here, and here, that 4 delta x on the top and this delta x on the bottom also cancel out, so I can go like that. And so now I have the limit as delta x goes to 0, and I have 4 over square root of x plus not plus, it'll be times x plus delta x times the quantity square root of x, now plus square root of x plus delta x. Now, I know that that probably doesn't look a whole lot better than the last one, but if I let delta x go to 0, it doesn't make any of these multiplied terms 0, so I no longer have anything undefined. All right, so I can just let it happen. This becomes 4. When I let delta x go to 0, square root of x just stays square root of x. When I let delta x plus delta or x plus delta x go to 0, I'm just left with x, so I have another square root of x. And then I have a multiplication. This stays square root of x, and then it's plus, again, another square root of x. And so square root of x times square root of x is x. Square root of x plus square root of x is 2 square root of x. So I have 4 over x times 2 square root of x. A 2 cancels, so I'm left with 2 over 2, or excuse me, x square root of 2. Let's do that. 2 over x square root of x. That's what I want. And for this instance, that's just, there's my answer. Now, here's the thing, folks, and this is error management time. Notice I have written the limit in every step until I get to here, because it is from this step right here to this last set of steps right here that I am actually taking the limit. So since I have not actually taken the limit, I have to continue to write it until I actually do the limit. And the reason I say that is because every year I have a student who won't write the limit until every step until they're actually taking the limit, and they'll leave that part off, and then it's at that point that they end up missing the point. All right, so let's get to these last two here. I'm already up to 21 minutes, and I hope that I really didn't want to get it that far. This is a drawing example, and so essentially what I want to do here with this example is so given f of x, draw f prime of x. Okay, now here's some things. Here's the thing I want you to understand. I am drawing the slopes of the tangent lines. So think of it this way. My result here, my tangent line at 2, this tangent, if I were to draw that tangent line in at 2, it would be both positive and big. When I draw a tangent line here at 4, it's the value of the tangent line will be 0. And then if I draw in a tangent line here, the slope of that tangent line will both be negative and big. All right. So when I draw in f prime of x, it's not going to be, there's a lot of interpretation here, but there's certainly some things that I have to have. Any value for my tangent, any slope here is going to be positive along this part of the curve, but they are going to get smaller as I get closer and closer to 0. And at 0, the first derivative will be 0. So I could plot that point right now if I wanted to. I'll just put that in there. And then from then on, the tangent lines, the slopes of the tangent lines are going to be negative, and they're going to get bigger. So I have to have something positive and big at -2, something negative and big at +2. So just as a real quick guesstimate, here is going to be my f prime. Why? Because the slopes as x goes from negative infinity to 0, all have to be positive. So here's my slopes, they're all positive. What are they doing? They're getting smaller and smaller and smaller. These slopes, as I get closer to 0, get smaller and smaller and smaller, but they're all still positive. At 0, I have a horizontal tangent line, so the slope of that horizontal tangent line will be 0. And then as I go away from x towards positive infinity, the slopes are going to start becoming more and more and more negative, and they're going to keep getting bigger. And so that's going to continue to go down. Now, if this is a quadratic, I guarantee that's a line. If it's not a quadratic, it may not be a perfect line. All right, my last one of the day. Let's see if I can get this done. Okay, real quick here. Example number 50, or page 105, number 54, it says that it wants you to take this expression and say that this is the first derivative at a point. All right, so that is essentially f prime of c at a point, some constant c. So it wants me to find f of x. They want me to find, or actually they just say it's f. They want me to find the function, and then they also want me to find c. All right, so we know that the limit equation for first derivative as delta x goes to 0 is equal to f of x plus delta x minus f of x all over delta x. Okay, so I've got some things that I see here. And so the question says, well, let's find it at a c. Well, that would be f prime of c is the limit as delta x goes to 0, and there shouldn't be an equal sign here. Since this is going up on the web, I want to make sure that everybody knows that I actually know what I'm doing. So f of c plus delta x minus f of c all over delta x. So I look at this thing, and I see this negative 2. So it looks to me like that c is negative 2. And then if I were to, I've got this cube here, so there's another clue as to what I'm looking for. And if I take negative 2 and I multiply it by itself, let's see here, did I screw that up? I did screw that up. This should be a plus. Sorry about that. Make that a plus, make that change. And if I make negative 2 and I take it to the third power, I'll have negative 8, and if I subtract negative 8, it becomes plus 8. So just kind of working through what I see here, it looks to me like my c value is negative 2. And then the function, what do? Well, that function f is just going to be x to the third. And see, I can see that cube here. So just as a test, if I said find f prime of negative 2, given what I have here, it would be the limit as delta x goes to 0, and this is just a check of, let's see here, it would be negative 2 plus delta x to the third minus negative 2 to the third all over delta x, and we can quickly see that it is this expression, so I feel confident in those answers. Well, that was a little bit longer than I wanted to, folks. I apologize for that. It is 28 minutes, but that's all I have. We will have questions starting in class. Have a good day.